Today we're going to take a little back up and go back to section 9.7 that we skipped previously, and that was a probability section that was kind of misplaced in that chapter, but we're going to go back and look at it now. So it has a lot of important probability characteristics. So first of all, our little definition of a sample space. Let's just look at my example down here. Here's an example of a sample space if I roll two dice. If I'm particularly interested in what the actual rolls are for the dice, first one coming up a 1, second one coming up a 1, or the first one coming up a 1 with the second one coming up a 2. So I'm looking at the particular ways that the rolls can come out. And if we think about it, the number of items that will be in our sample space is there are 6 ways for the first die to come out, and there are 6 ways for the second die to come out, which means there will be a total of 36 different entries in my sample space. And this is kind of cumbersome to write all these down, but if you were asked to list the sample space, you would literally list down all the different ways that the event can take place. So if I were rolling two dice, there would actually be 36 outcomes. Now, on the other hand, if I was rolling two dice and I said write the sample space for what the sum of the two dice could be, then we would list down, well, you can have a sum of 2, you can have a sum of 3, and I would write all the integers down from 2 to 12. So you have to read the question carefully to see how it's being asked. But if I look at just the particular sample space without any other information for rolling two dice, it would be all the individual ways that the dice can come out when you roll them. And we know that probability of an event is always some number that can be as low as 0, meaning that the event can't happen, to a number as high as 1, which means the event will always happen. And then it can be different values in between. However, that's the likelihood of the event taking place. So if we have a number very close to 1, it means it's very likely for the event to take place, as opposed to if it's very close to 0, then it's not very likely for it to take place. And if each of these little outcomes here in my sample space that I listed here is equally likely, then the probability of a particular event will be to count how many ways I can have the event happen out of the total number of items in the sample space. So for me, we'll look at this next question. If I wanted to find what's the probability of rolling a sum of 8, the probability of rolling a sum of 8, if I look in my sample space, I know I have 36 items in my sample space, and if I look at those that have a sum of 8, I can see that the 2, 6, 3, 5, 4, 4, 5, 3, and 6, 2 are items that work. Therefore, my probability of having that happen is 5 out of 36. On the other hand, if I wanted to find the probability of rolling a 3 on the first die, again, if I'm considering my event to be I'm rolling two dice, then there are 36 different outcomes that are possible, so my denominator 36, and I would look at how many of those have my first die coming up a 3, and we can see that these are the different ways that it can happen, and there are 6 of them out of 36, or a 1/6 chance. Now, a couple of definitions. First of all, if we want to find the union of two events, so this symbol U means union, and if I want to determine what the union of two events occurring is, first of all, the two events would have to be from the same finite, means accountable sample space. So I can't talk about event A being rolling two dice and getting a sum of 3, and B be the event that I flip a coin and get heads. I have to have these two come from the same sample space of events. But if I want to find the probability of the union of these two events, I can also replace the symbol union with the word or. So union and or probability of A union B means exactly the same thing as the probability of A or B. And that probability statement looks like this. That we actually, first of all, find the probability of A, and then we find the probability of B. We add those together, but then we have to watch out for overlap. And I have a little Venn diagram shown here. Let me just quick draw the picture of the Venn diagram by itself. If we want to find the union, again, I take the probability of A, and I find the probability of B, And I will add those together, but you can see if my two events can happen at the same time, I'm going to double count this region. And we call that region where they overlap the intersection, and that is written as the probability of A intersect B, or we can also put the word and in there. So and means intersection, or means union. So that little picture, anytime you think of the union of two events, that means either the first event occurs or the second event occurs, or both of them could occur. So anything in that shaded region, we just have to watch out for double counting anything. Now sometimes our sets don't actually cross. If that's the case, we call them either disjoint sets or we call the two events mutually exclusive. So here's a picture of the Venn diagram with that. So if I have two events, A and B, who can't happen at the same time, we say that these two events are mutually exclusive, or we call the events disjoint. And we can see that in that case, the probability of A intersect B happening will be 0 because they won't be able to happen at the same time. So let's look at a probability statement. We'll write out some things formally, and sometimes you can kind of intuitively figure out some answers, but we'll do them formally so that we can see how our formulas are working. If two fair dice are tossed, what is the probability that we would get a sum of 2 or 3? And again, here's our formal way of writing it out. We'd find what's the probability of getting a sum of 2 or 3. Now I could have also written that union symbol there, the U. And to find the union of two events, I find the probability of the first plus the probability of the second, and I subtract away the overlap. And again, this and, I could have intersect symbol in place of that word and. Now, we know from our table up above, or our sample space up above, that there is one way to get a sum of 2. We know that there are 2 ways to get a sum of 3. And it's impossible for you to get a sum of 2 and a sum of 3 at the same time. So these two sets are actually mutually exclusive. They cannot happen at the same time. So this intersection just won't be a probability of 0. And so we get our final answer. Let's flip. Now naturally we need to see an example where we have an intersection. And here's the idea if I have a deck of cards. And if I have a deck of cards has 52 cards, and half of them are red, half of them are black. And we have some face cards. Your face cards are your jacks, your kings, and your queens. And we have 4 suits. We have diamonds, hearts, clubs, and spades. And if I asked you if you draw one card from the deck, what is the probability of drawing a red card or a face card? I see the word or. I know it's a union. So I know I'll have to find the probability of red plus the probability of a face card, but I always have to watch out for overlap, where I've double counted some cards or I've double counted some probability. And I know that half of the cards are red, but I'll put it out of 52, so there are 26 cards out of 52 who are red. My face cards, I have 4 jacks, 4 kings, and 4 queens who are face cards, so I have 12 cards out of 52. However, I just double counted. I double counted all the red face cards, and that is 6 cards, 2 jacks, 2 kings, 2 queens. And so I end up getting my probability of 8/13. So in this case, these two events were not mutually exclusive. They did have overlap. They are not disjoint. Disjoint set would mean that they don't cross, they don't have any overlap. Now another topic that can be very confusing for people is the idea of independence. It's not confusing as far as what it means, but sometimes people will get it mixed up with mutually exclusive. So the idea of independence is that if we have two events, and if two events are independent, that means that A and B do not affect the likelihood of each other occurring. So if I knew A happened, B would happen equally likely whether A did or not. And same thing goes through the opposite way. B is not anyhow impacted by what happened with A, nor is A impacted by what would happen with B. An example of that would be if you flip 2 coins. And if I flip one coin first and I get heads, The second coin does not care that the first coin came up heads. It is equally likely to come up heads or tails regardless of what happened on the first occasion. And we have a test for finding whether two events are independent. And what we do is we look at what is the probability of their intersection. And mathematically, if the number of ways that they can come out together, or the probability of them occurring together, is equal to the product of their two individual probabilities, then the two events will be independent. Now, sometimes we don't have independent events and we know it at the beginning. And we'll write the formulas down for what happens if you don't have independent events, and you'll see that you actually know these, you just don't know them in the symbols that I'm giving. So if two events are independent and you want to find the intersection of the two events, it will be as simple as find the probability of the first event, find the probability of the second event, and you don't even have to regard the first one ever taking place, and just multiply them together. So I just gave that up above. Now, on the other hand, if you know that A and B are impacting each other, that are affecting each other somehow, then to find the probability of the intersection, you find the probability of the first one, and then you find the probability of B, and then you write a line down, and that means the word given. So we say this as find the probability of B given A already occurred. And that's called a conditional probability. And again, you have worked with it, you just possibly don't realize the symbolism. And likewise, it can be found the opposite way. If I want to find the intersection, I could actually find the probability of B first, and then multiply that by the probability of A happening, given that B already happened. And again, once we go to an example, this will make more sense. So we want to look at these events and find out whether they're mutually exclusive or not. So we'll go back and look at that definition first. And remember, mutually exclusive means that picture-wise, you have two events and they cannot happen at the same time. So rolling an even number or a prime number on a number cube, meaning a die. Well, an even number obviously is going to be the 2, 4, 6. Prime numbers are numbers who are bigger than 1. So the prime numbers, when we roll a die, would be a 2, a 3, or a 5. And we can see that they have overlap. Therefore, these two events are not mutually exclusive. On the other hand, if I say rolling a prime number or a multiple of 6 on a number cube, well, we know what the prime numbers are. And multiples of 6, not factors, but multiples of 6, the only multiple of 6 is 6. So these two sets do not overlap. They are mutually exclusive because they have no intersection. Here's a little example of working with some probability again. Just another example of what type of question you'll encounter. At a restaurant, customers get to choose one of 4 vegetables for any main course. About 33% would choose green beans, and about 28% would choose spinach. What is the probability that they'll choose beans or spinach? Well, they only get to choose one. Therefore, we can just add these two probabilities together. There is no intersection. These two events are mutually exclusive because they only get to choose one. Now, if they could choose more than one, we wouldn't know what the overlap was from the wording of the question. Close to done. Number 8. We have a box that contains 20 red and 30 blue marbles. Okay, so I drew a little picture. We have a second box, and it has 10 and 40, 10 white and 40 black. And we're going to choose one marble from each box without looking. And we want to find the probability that you get a blue marble and a black marble. Well, we're picking one from each box. So we want to find blue and black. We want the intersection of those two. But notice that these two will be independent because the likelihood of you pulling a blue one out of this first box is going to have absolutely nothing to do with pulling a black one out of this box. So we can just find the probability of blue times the probability of the black and get our intersection. Now we're going to choose 2 marbles from the first box without looking. So we're just going to choose from this first box. And this time we are not going to be replacing the first marble. So we want to find what's the probability of drawing a red on the first draw and a red on the second one, but you are not putting it back. So I am doing this dependently, and here comes our formula. We find the probability of drawing a red the first time. But now we need to find the probability of drawing a red the second time, given that we already drew a red the first time. So this is called a conditional probability. And what's the likelihood if I drew a red the first time? 20 out of 50. And think how many now are left in the box and how many of them are red. So we can figure out what the conditional probability is. There will only be 49 left in the box, of which 19 will be red. And then we can find out what that probability is. So this is not an independent situation. It's a dependent situation because me taking one out and not putting it back affected the likelihood of red the second time. Now, on the other hand, if I look at this last one, if you choose 2 marbles from the first box without looking, however you replace it after you pick, we want to find the probability that they're both red. And in this case, I do have independence because when I pick a red the first time, I put it back, and I have an equally likely chance of picking a red the second time. So me pulling a red one out the first time had no impact on this one being red the second time. So I have an example of independence here and non-independence. And we'll talk a lot more about this, the idea of the difference between independence and mutually exclusive as we go. But basically, if you have mutually exclusive, your 2 sets will not intersect. If you have 2 sets who are independent, they will intersect. But this intersection will be special, and this special intersection will end up being the product of their probabilities. And we'll have a worksheet that will work on that in a lot of detail as we go. So now you're ready to work.